Welcome all to the new lecture of Digital Control in Switch Mode Power Converters and FPGA based prototyping course. This lecture will be in continuation with the last lecture and it will be again focusing on STM32CubeMX. In the last lecture we discussed the example of GPIO toggling. In this lecture we will be starting the example of UART communication and it will be demonstrated over STM32G4 Nucleo board. Then we will be covering the key peripherals initialization required for digital power applications, mainly the ADCs and the timers. Then we will be focusing on the advanced setting where we will be covering the difference between the hall layer and the lower level layer. And in the end, we will be focusing on the digital power workbench. Let us start with the UART communication example. Here we are using an hyperterminal where the Nucleo board will be exchanging the data. We can directly go to the repository and open that particular example, but if we are not aware of the examples available, we can go to the access to example selector. The beauty of this option is here on a single screen we are able to see all the firmware examples available for that particular Nucleo board or the discovery board that we are having. So we can select the STM32G4 microcontroller. So all these are the examples particularly for the G4 microcontroller. These are the ADCs comparator examples. So we can select any of these examples depending on our requirement. So corresponding the IOC file will be opened. Also the firmware project is already there, so we need not to generate the code again and again until unless we require some specific change. So let us go to the repository directly. So this is my repository. I will be going into G4 version 1.5.0. In this, I will be going on to the projects. Then I am using Nucleo G474RET6. In the examples, I will be going to UART Peripheral. And within that, I will be selecting hyperterminal and interrupt example. Before jumping onto the project directly, I would request every user to go through the readme.txt file before exploring any of the examples. It tells what all pins are configured, how exactly they are configured, and also the basic details that what the end user can expect that basically the end results from that particular examples. Also in some examples there are some settings that need to be done, like in this the hyperterminal settings that we need to do is given here. So it is beneficial to go through readme.txt file for any of the example use. So let me copy the path of the project and open this in IAR. So I'm flashing this code into my Nucleo board. It will be taking a couple of seconds. So the firmware is flashed. So I'm stopping the debugging here. Now for the hyperterminal, I am using a TerraTerm tool. While you can use any of the hyperterminal tool, but we need to aware of the settings that we need to do. These settings are present in the readme.txt file, also in the main.c file of your project. So I have done the setting. So if you can see the Nucleo board, I am just pressing the reset button of this and you can see my hyperterminal window. It shows hyperterminal communication based on interrupt. Enter 10 characters using keyboards. So I am typing just 1 2 3 4 5 6 7 8 9 0. So as soon as I entered, it says example finished, and whatever the data I have entered, it has displayed. So we have completed the hyperterminal interrupt example. So the idea behind of showcasing this particular example, and similarly there are several other examples which we can use, and on top of it we can build our application depending on the requirement or the configuration required. Now we will be switching on to the key peripherals that are required within the digital power applications. Digital power applications are very much timing critical. There are several analog signals that need to be sensed, and they will be processed within the microcontroller, and accordingly the right signal or the right PWM need to be generated to switch on or off our MOSFETs. Along with that, in our hardware there are several comparators and op-amps to have various comparisons sensing with appropriate gain. For any digital power application, we need to make sure that the MCU clock is fast enough and the firmware or the code written inside it should be highly optimized. It can be done by using lower level libraries so that every command can be executed in a very less clock cycles. On the screen we can see STM32G4 microcontroller, which contains all the peripherals required for any digital power applications. On the left side we see all the peripherals it includes. Let us take one by one. In the system core, we have already discussed that it includes the GPIO settings, the interrupt settings, the debugger settings. The most important are the analog sections, which includes the ADC, comparator, DAC and the op-amps. The advantages of having the op-amps and the comparator inside, not only in terms of cost but also the space is optimized and we can adjust the various gains inside. In the timer section, we have the high resolution timers, advanced timers, some low power timers and several other timers. The high resolution timers is having the resolution of 184 picoseconds, where it can be configured and interlinked with several other peripherals, basically some external events, to make it work as an independent state machine. So when we say the statement that the digital power application is very much timing critical, so these high resolution timers and their interlinking with the external events is very much helpful. Apart from that, there is the connectivity in which we have the UART, SPI, I2C. So these communication channels can be used as per the requirement. Apart from that, we can use the middleware, computing, security as per our user applications. Though they are not very much required in the digital power applications, but if required, we can use it accordingly. Time and again, we are highlighting that digital power applications are very much time critical. So there are some advanced settings in which we can have the best of the optimizations in terms of code. So let us go through those settings. Before we enter into those settings, let us configure few of the pins with different peripherals to explain better. So just let me configure one of the pins as the timer, and let us take one SPI. So now we have three peripherals, basically SPI, GPIO and the timer. So on the dark blue, we are on the pin and configuration page. So this is the second one, is the clock and configuration. This we have already discussed in the last section. The third is the project manager option. So by default we see this page where we can enter the project name, the location and other things. And in terms of the firmware package that we want to use, the package we have already downloaded, we will be able to see it here, but just in case we always want to use the latest version, so we can check this option. Also the stack size, that can, if we want to change, it can be updated here. Normally it takes a default setting of the microcontroller that we have selected. The second option is the code generator. So in this there are again several options depending on the user requirement. By default all the libraries files has been added in the project folder, but in case there is some space constraint, we can use copy only the necessary library files, and similarly other options can be chosen. The third option is very important. So if we select this option, set all pins all free pins and analog. So basically all the unused pins will be configured as an analog if we select these options. So this will be optimized in terms of power. While if you go on to the advanced setting, this is again a very important section. In this there are options of selecting the drivers. So basically let us take an example of SPI. By default hardware abstraction layer is selected as a driver, but if I want to use the lower level libraries, so basically the lower libraries are much more optimized. We can directly write the registers. It takes less clock cycles of the microcontroller to execute the commands. So this is very important for the digital power applications. I would suggest we can start with the hall layer to have a better understanding. Then as we have more understanding on the STM32CubeMX tool, more understanding on the firmware, then we can select the lower level libraries and optimize the code, and accordingly we can see the difference. The last section is the tools. Here we can see the power consumption and other things, as we have not configured all the peripherals, but if we can configure as per the requirement, we can see that what sort of the power consumption and the stop convention, basically different modes, what sort of the microcontroller behavior will be there. So this we can explore, but we have to make sure that all the pins of the microcontrollers are configured as per our requirement. Then this tool page is very much important for us. Based on STM32CubeMX tool, there is another powerful tool from ST Microelectronics, that is Digital Power Workbench. So I am on ST website. If I go on tools and software section, and within the first section I could see the e-design suite. In e-design suite, if we scroll down, we can see the digital power workbench. We can click on start design. This is the very much new tool from ST Microelectronics. Right now we have the full bridge LLC converter with synchronous rectification. It is based on STM32F334. More and more topologies and more microcontrollers are being added. So without changing any specifications, it's a 3 kilowatt configuration. I just click on start design. So it has already taken my login, but if you want to do the login and make some changes in the configuration settings, or you want to update the power rating or some other MOSFETs you want to explore, you can just do the login. And the most important thing is here, when we go to the specifications, the last option is the firmware download. So here we can download the firmware. So it will be downloading your complete firmware package along with the STM32CubeMX IUC file. There also you can do the certain changes and make your application work. Concepts covered. In the last lecture and in the ongoing lecture, we have covered the features of STM32CubeMX software tool along with some examples. Also, we have discussed key peripherals required for the digital power application. Then we have discussed the advanced settings, particularly the hall layer and the lower layer differences. Then we also touched the digital power workbench, particularly for the LLC application. While in the upcoming lecture, there will be live demonstrations of digital power solution with power rating in the range of few kilowatt. Thank you. See you in the next lecture.